What's up, guys? Engineers for Communities, Microcell here. I am super stoked. We're going to go over Lift Station 101. Why does it matter for you and your community? And it's going to be a really exciting day today. We're going to go over different example calculations, what the different components of the lift station are, as well as what is typical operational and maintenance guidelines that you should be trying to follow. So what is a lift station? A lift station, otherwise known as pump station, depending on who you talk to, it's a very critical component of the sewer system or your collection system for your wastewater. What it does is it will collect water and store it within some sort of basin over time. And then once that water is filled up to a certain point, it will then pump that water to a point that's at a higher elevation than where it's at, sometimes going back into your collection system. Sometimes it goes directly into the wastewater treatment plant. You see these installed a lot of times in areas that are super flat where you can't really gravity flow wastewater over to that area, or it's hilly. So there's just tons of hills. So you've got to get this back up to the top of the hill so it'll flow over the hill into the collection system to the wastewater treatment plant to get treated. All right, so how do lift stations affect you? Well, there's a lot of different things. They're typically over certain flows. They're regulated and reviewed by your state or local governments. It's very critical in your infrastructure planning and development to identify where you're going to be placing lift stations in the future or today to help water get to one centralized point for your wastewater treatment. They're very important for the public health and safety. So we want to take this sewage and not let it, like this picture here, just go straight into some sort of creek. We want to be able to collect it and safely get it to a treatment plant. And then lastly, cost efficiency. So, making sure that when you're designing this, you're using cost-effective solutions, whether that's some sort of package lift station or just picking good pumps or something to that effect that can help you save money over the long term. Okay, guys, I want to go over the key components of a lift station. I've got this nice diagram to help me kind of navigate it. So right here, we've got the wet well itself. So typically it's concrete, but it can be fiberglass or some other material, HDPE. That actually houses where the fluid will go. We've got the pump itself. So right here is the mechanical device, the pump. It's run off electricity, and that's what's going to move the water up and down. In this image, the pump is actually in the wet well. Sometimes they have a suction intake, and then over here on the right, that's where the pump will be outside. There's different advantages to having it in or not. Sometimes, for example, the fluid of water will help keep the pump cooler and help with some of your efficiencies there. But having your pump outside of the lift station and not in all the sewage, it could not get caught up in different rags and stuff, or it's also a lot easier to maintain. So then we have the pipes themselves. So here I've got the inlet pipe. This inlet pipe right here has an elbow that puts it all the way at the bottom. Sometimes the water, if the inlet's low enough, it will just come straight in. In this case, it's coming down an elbow. And then here, another pipe, I've got the discharge piping here. So essentially the pump gives the water into the discharge pipe, and then it goes into its ultimate location. Control panel. So up here, I've got the control panel. It does a couple different things. One, it will it'll open and close different circuits so that the pump can turn on and off. It also will supply electric signal to different components like your alarms, your monitoring systems. It's also a lot of times tied to your SCADA. So there's some sort of component in there that sends a signal to a remote operator, whether it's via a satellite or some sort of radio antenna or phone lines, cell lines, and it will tell them so that they can monitor different inputs that are being measured in the lift station, typically whether the pump's on and off and what level the water's at. Maybe even there's a flow meter telling you how much water's coming in. Power supply, a lot of times it's kind of hooked up along with the control panel, and then alarms, warning systems. So that here I've got what are called floats. There's many ways to measure the different elevations of the water in the lift station. Three main ones would be floats. So that's what you're seeing here, floats. You can have a pressure transducer, so like a hockey puck sitting down at the bottom, or you can have some sort of ultrasonic device that hangs from the top and it takes a signal down. The simplest, most cheapest one is usually these floats. So these floats are just like little rubber pieces. As the water hits it, it essentially talks to the control panel and then triggers certain events. So in this case, when you hit 1, that's when the pump's going to turn off. When the water level gets up to 2, the pump will turn back on. And if it's still going and you've got a duplex system with 2 pumps in there, that it hits 3, it'll start turning both pumps on. If it hits 4, then we're going to get an alarm signal sent to your operator until it pumps it all the way back down to 1 and it turns off. There's different valving. Sometimes you'll see like a check valve on the back of the pump here or on this portion so that the water, if the pump's off, it's not coming back through the discharge pipe. You may have a gate valve on the discharge out here or on the inlet. Or if you've got overflow piping, you may have some sort of gate valve to close off your overflow area so that you can pump it out. And then backup systems, it's not in this image here, but you'll see different generators that are either like gas, propane, something like that. I'll show you later an image of one that turns on when we lose power to our system. Okay, so I've got a link in the description to this spreadsheet. Feel free to use it. Obviously, use at your discretion, back check any of my assumptions and calculations. This is to be helpful and be a tool to be used, but not a end-all option for your engineering to say this is the truth and this is going to get you the exact right answer. But here's my spreadsheet, and what I'll do is I'm going to go through a presentation here, and we will share that link with you and enjoy. Hey guys, Big Mike here. I wanted to go through how to set up wastewater lift stations that have some force main, but typically simpler tasks that don't quite need to be required by advanced modeling software to determine what you need. So going here, I'll go to the kind of existing site plan here. This is a Florissant, Colorado, and we have this existing lift station here that we're going to replace with a new lift station right next to it. We'll connect to the existing 4-inch force main, and we'll essentially use that in our calcs. And we're going to connect to the new wastewater treatment plant. Well, it was new at that time, but these are the as-builts for it. So you can see here's where the pipe comes in, 13 feet above the bottom of this tank. So I like to kind of work things down. Projected pump flow, this you'll actually kind of iterate through. For this exercise, I started at like 90 GPM. Force main size, got 3.79 inches, and where does that come from? Over here, I had some Schedule 80 PVC pipe, and I'm able to pull in, what's that pipe diameter? So if you come to 4-inch, it's 4.5, but the inner diameter is 3.786. So you see it's 3.9. Working down more in my spreadsheet here is we're trying to figure out the properties of this force main. Things like the cross-sectional area are automatically calculated based on the force main diameter. This incoming peak flow rate, for this TDH sheet, we just use the flow that we project above. Length of force main, so in this case, I went and I measured the length here, so I had 787, and the next segment was 547. So in there I just added those two, 787 plus 500, and we got 1,287 feet, and that gives us something you always want to be checking is what is when you have an on-off pump, what is the velocity in that force main, because you'll want to be over 2 and really over 2.5 during your normal flow, because that will help flush the line and stop it getting clogged over time. So moving down, I have a couple different inputs. I have the minimum water level here and the max water level, and those will correspond to where the water goes up, like where the minimum water is in the lift station, and that actually corresponds. I'm going to show you my lift station section to get an idea. That's the lowest level that the water will normally pump at. So you see here, low water level. That's right there. During normal operation, there's always water in there. And in this example, this wasn't the finished one. High water, so essentially the pump turns on here, and then it pumps it down to here. So at high it turns on, it pumps down to low. So yeah. So that's what those elevations are. These are in red because they haven't been updated on the plan sheet, but in this example, the minimum was 8128.57 and 8130.15. Now, the pump elevation is going to be the bottom of the wet well, or it's the actual elevation right here that it sucks it in at. The next input on the spreadsheet is the force main's max elevation. So in this case, the highest elevation this force main pumps to is in the wastewater treatment plant. And here, if we go to that hydraulic profile, you can calculate it. So I have 8128, 8182.25 plus 13.5 feet, 8195. 8195.75, 819.75. So we're good there. And then essentially what you can do is you can take the total head from the suction of the pump to the highest elevation, and that's what you'll call your static head. It's always there. The pumps always have to work against it. And you'll see a graphical representation when we get down to the end of the spreadsheet. So the next step you'll want to do is we use the Darcy-Weisbach equation, and there's a couple different inputs here. Velocity, which it's going to be, we've already calculated right there. Head loss, it's calculating the head loss due to friction, which is just proportional to the length of pipe. So you've got length of pipe here. We've got the velocity right there. The coefficient of friction, so this is an older pipe, so we used 140. If you see, if we go up to 150, it goes down. So it's an older PVC pipe. I think it's like 20 years old. So we use that diameter. That's just going to pull from the D up here, and then it will calculate the static friction head loss. The next thing you'll do is you'll do all your minor head losses, and here's the equation for that. It's k times the velocity squared over 2 times the acceleration due to gravity. Acceleration due to gravity is constant. K, you'll want to come in and count up right here. You see I have this force main tab. You'll want to come in and count up entrance, exit. How many 45-degree bends do you have in your main? How many 90-degree bends do you have? Do you have any valves? Stuff like that you'll want to get added in there, and you add them all up. In this case, it added up to 3.5, and so it'll actually take the 3.5 there and do it. There's this required discharge head, so if they're wanting additional head on the discharge, so we want to add an extra 5 feet ahead for whatever reason that they need the water to be shooting out of the pipe, you can add that in here. Normally, like it says here, typically for force mains it's 0 because it's just pumping and just needs to come out at just atmosphere. So total dynamic head, okay. So we already calculated the static head up here. Total dynamic head, we're just going to add up these 4 columns. And that's what's going to get you the total dynamic head. So 89.5, we'll call it 90 feet. So we've gone through the minor loss table. Here I've got this static loss table. So this is just an auto-generating table. It's going to take that pumping number that we've set up here, and it's just going to auto-populate the rest of the table. So 140, it's just going to take the 140, it's going to go to 0 at these even increments, and then it's going to double that to those increments. And here's the equations, the same equations and everything from before. You'll see some columns, it does the max water level, the minimum water level. Here's the max and min on the end that you'll see. And you'll see where this comes into play here. When we come to our system graphs, there's a high and low water level that represents max min of our operating ranges. So let's go to the system graph here. So there's a couple different graphs, and the yellow graph represents the low water level. It's kind of confusing because low water level is on top of high water level because it requires more head because the water's lower, so it requires more head to get to that location. And the green line is high water level, which is when the water is at that high water level elevation here, and that's why it's below. So that's that. And then down here, what I've done is I've created a separate chart for what I call the pump header losses. So typically in your lift station, you'll have piping that is smaller than the piping going to the force main. In this case, I believe this is 4-inch pipe, and so we wouldn't need to say it was 2-inch pipe. it makes a big difference. But it's its own. Sometimes you can have 2-3 pumps pumping into one force main, but when you're adding up all the different pump heads, and if you have different sizes of pump, you'll want to do its own calculation on the side, and you'll see where we use that later. So yeah, that's this gray line down here. It's very small, and it's calculated in the pump selection table down here, where a different head loss is being calculated for each curve. Next part here, so we've talked about the system curve, how that's generated. So once that's generated, you start going through an iterative process. In this case, what we did was we called up the pump rep. They had Willow pumps, and we went through a couple different iterations to figure out what pump is going to work best in this lift station, and can do things, work in an efficient range and such like that. Because this was such a statically head-driven system curve, it's hard to find pumps, so we went through a lot of iteration. So I'll go through this next tab here, pump selection. There's lots of stuff highlighted in yellow for inputs. So what we did is we went with a bigger pump to work closer to the left side of the curve instead of the right. In this situation, they actually had pumps that were operating on the right side of the pump's curves. And let me actually pull that up. I will show you what I'm talking about here. So this is a pump. This is that Willow pump right here. And you can see that they actually selected a point on the left, but the existing pumps were far to the right. And when you're far to the right, you're consistently pulling more power. As you can see, you're moving more power from the pumps further to the right than on the left. So we picked one to the left. We couldn't find a pump to work in its BEP range for this system, so we picked something that was on the left side. That's why you'll see these flows that just don't match up here. But I'll still go through this tab on the spreadsheet. So Willow pump, 7.4 horsepower. The impeller was selected, was 10-inch. Hertz is 60. So I'll go through these. So what I've done is I've created these Hertz tables, and they're all just based on these yellow inputs. So you don't have to, once you set up the equations, you don't have to set it up again. So you type in the BEP, that one's just straight off the manufacturer's sheet here. And then I typed in a bunch of different points for the flow and heads that were from their curve. So I could come on here, I'd pick a flow, pick a head, and I'd pick that point right there and then type it into the spreadsheet so that I could draw in. Okay, so continuing onward, I've got the 10-inch impeller here, and you can see that reflected here. So yeah, like I mentioned, all these, you can calculate your different BEP flows for the different. If you have a VFD, you can vary all these hertz, and so that's what you see here. It pretty much is just taking this number inputted from here, and it's calculating a VFD part. So there's this thing, I have this thing called BEP box, and it's auto calculating. It's using these rule of thumbs that you want minus 20% to the left or 10% to the right of the BEP for your thing. So let me show you what that looks like on here, just so, because it doesn't show up at this scale, but I can format the major accesses, and actually it's not on here. Let's go here, select data. I think we turned them off. Okay, the boxes are on here. So format plot area, format access. So we want this to go further to the right, so I'm just going to go to 500. So there you go. So there's this box here, and that's the BEP for this 60 hertz for this pump. So it automatically draws it in. But like I said earlier, we're trying to operate to the left, and so that's why this is over here. I'm just going to undo that. Okay, so moving down here, I draw these two lines, and this is kind of iterative. I just type in this first number. So actually I can unhighlight these and keep that highlighted. So it's actually just these ones that get changed, and boom, it's just drawing in these lines to see where one or two pumps, where they would auto operate. So yeah, let's go back to that modified pump curve concept. So length of pipe, that's the length of the pipe, the header pipe. The diameter of the pipe, in our case, is 4-inch. We go back, look at that table. 4-inch, and then C value 140 steel pipe or older PVC. So we could actually go up to 150 on this, which will slightly affect the numbers, but not a lot. And then down here, there's, as it says, create a separate system curve direct to represent the expected head losses in the line. So we're only using this 60 hertz, but it can be calculated for all of them. And so then down here, you have what's called the modified pump curve. So you'll see this dashed line and this red one. And with a single pump, all it's doing is it's taking this value here that we calculated, and then it's taking the pump value S8, which in this case S is over here because we were looking at some impeller trimming, and a different one, and it's just taking those and subtracting it down instead of doing something funky with the system curve. And so that's what's going on there, if you're curious. And that's it for the pumps. You had to go through that iterative process and figure out where it's going to work. You got to check to make sure the velocity is working. So the last thing I like to check is the cycling, the timing of these pumps, making sure that we have enough volume in the wet well. So what I've done here is graphically drawn the critical elevations for our wet well. And it's very iterative, and we've got overflow pipes on this. So I'm going to go to the site plan. You can see here we have two buried overflow pipes for this. That's going to vary for every city, municipality, state regulating authority. In Colorado, it's kind of vague, but they generally like to see a couple hours of overflow capacity. So what I've done here, this is, like I said, this is the bottom of the wet well, pump off. This is low water level. Right here, high water level. And so what happens is this is where the pumping starts. It's 0. So you see zeros here. And then everything goes off of it. So it takes, at the peak flow, if we're peak flowing, you'll see cycles per hour. So let's start from here. So it takes 2 minutes to fill here. And all it's doing is taking the difference in those two, So it's saying it takes 2 minutes to get there, and it takes 4 minutes to get here. So that's why this is yellow. And it says cycles per hour. So one of the things you want to look at is how many starts per hour you're allowed to have. Here it's 10 per pump, so that's 20 starts per hour. So if we're getting to this point every 4.5 minutes, and it takes 10 minutes to pump it down, then that means a cycle is about 15 minutes. So if you took these two numbers and you went 4.28 plus 10.30 and you divided it by 60, and then you did 1 over x, that's how you're going to get this number of 4.1. And then if you use an alternator, it's alternating pumps. So actually each pump's only getting turned on twice per hour during the peak flow. Peak flow number here in this case was 2.5 times the average daily flow. And the average daily flow is 40. Where these numbers come for in this came just straight from the design of the wastewater treatment plant. Average flow for the plant is actually 40. And the peak flow is 99. And I had to actually go back to some old different documents than those plans to get that number. I think it's actually on the, if you go to here, average daily flow 0.057. So you would take, and this 0.1426 is equal to 99. It's pretty much 99 divided by 2.5 in this, which is 40, but it's right here you see this is 2.5. There's a peaking factor of 2.5. So I took average daily flow there. That's how I came up with the 40. 99 is just that number times 2.5. 40 is those. So moving on, the average. So we're doing the same thing, average daily flow, and then we created this green one here where like the pump's critical, if we had a flow that was half the pump. So if we're pumping 140, which is what we have here, this is 140. If we're pumping at 140, the critical pumping is at 70 GPM coming in. So what happens if we're at 70 GPM? How many cycles are we going to get? 2.5 per pump, or 5 if the alternator is broken. So all these numbers are below 10. All right, so last piece here. we have the overflow pipe. So what you're going to want to do is create an equation. Now these elevations are not exactly line for line matching up over here with this picture on the right, but essentially what it's doing is it's taking these volumes and the diameter of the pipes and correlating it all together. So you see it says length of pipe 60, it's 30 feet because there's 2 pipes, so 60 feet total, 4.5 foot diameter, here's the radius, and essentially the rest is using the different equations to calculate those overflows. So that's in a nutshell how you do your lift stations. So best of luck. Okay, so I want to go different operations and things to think about once you have your lift station installed and what you should be looking at. So first thing is, do you have an operation and maintenance manual, an O&M, some sort of training document that really guides the operations and preventative routines we should be doing, as well as an emergency preparation plan for when something happens? So a lot of times you'll either the district or a city will own the lift station and they'll have their own operators. And a lot of times here, it could be a privately maintained and owned lift station, and that's run and contracted out to a third party that operates and maintains several different lift stations and other water, wastewater components around your state. So regular monitoring, that kind of goes back to earlier. We talked about the SCADA system in your control panel and checking, okay, how's the levels doing, having someone kind of be on alert and making sure everything's working. And then also kind of just monitoring and going and looking down in the wet well at the components, periodically running the generator, making sure it still works. Next one, scheduled maintenance. So on the next slide, I'll go over in detail about what kind of things you can be maintaining and how long you would expect them to live, given good maintenance. But you want to be thinking about that backup power. So right here, you've got on the left side, this is the generator. And in having one of those that's just like on an automatic transfer switch is just such a ease. You can sleep at night. And a lot of times it's required on lift stations by your state governance. And like I mentioned up above, emergency response plan. So what are we going to do in an unexpected event? What happens when the pumps fails? Who do we need to notify? How do we get the power back on? What happens if the generator also isn't working? What are we going to do? And then record keeping. So how are we keeping records of how the lift station's been performing, how old each part is, what kind of maintenance we've done, so that we can always go back and look and see, okay, this part is this old and all that stuff. Okay, so what kind of components should we be maintaining? I'm just going to kind of go through again a lot of them that we talked about earlier, what the components are. I'm going to talk about their lifespan. So the pumps, it's pretty normal to have pumps last around 10 to 15 years. That inspection is going to be pulling the pump out, looking at it. There's different seals, checking the impellers, seeing if those need to be resurfaced, and adding any kind of lubrication, kind of like you do with a bike. You got a bike, your chain gets kind of hard to move and not smooth. Sometimes you've got to add some sort of lubrication. The control panel, just having someone come in and check, do all the breakers work, everything in there looking good, 15 to 20 years. Float switches, those tend to get lots of different rags and stuff, especially wastewater. And so they won't last long. You might want to change them out every 5 to 10 years and checking to make sure that they're not getting just pulled or the sensors are being blocked or anything like that. The pipes, both kind of the pipes and the wet well, I know it says 50 to 100 years. Some people that do HDP pipe will tell you it for sure lasts 100 years, and PVC pipe people will tell you the same. But if you take care of your pipes and the wet well itself, those two components, they can last a really long time. They can outlast you. So some things you could do is inspect them, have a camera go in there and look at it, repair any leaks and cracks, do lining. I think we talked earlier, other videos about the advantages of CCTV and then doing some sort of lining. Then your backup generator, regular maintenance is going to be someone coming in, turning it on, checking to make sure the fuel source is still good, different coolants. I'm not an expert on generators. I would consult someone specifically on what that looks like. Well, thanks guys for listening in today. I hope you guys learned something and are able to use this information to your best. I'll see you on the next one.